All right. Hello, everyone. Welcome back to Physical Geology 1404. How are we doing? 1403. You're not in 1404 yet. 1403. How are we doing?
Excellent.
Pretty good. You got a snake, so you're good. You're good. We're good over here. No? Oh, what's going on? You still stressed out about the lab? It's okay. We can talk about that today.
About sedimentary rocks.
She doesn't want to learn about sedimentary rocks. I'm sorry.
Fair enough.
You're gonna. We're going to talk about it today. Today is about sedimentary rocks, lecture 6. But before we do that, I have a few announcements. 1 week from today, if you are taking this class synchronously, later on, if you're taking my class and watching these recordings, it will be 2 lectures from now. Okay, we are going to have our exam 1 review session. Okay. So next time we meet, we will discuss metamorphic rocks, and then the time after that, we are going to have our exam 1. That entire day in class is devoted to getting you ready for lab 1, all review. Let me tell you something about the reviews in my class. I do not give you a review sheet. The review is dictated entirely by you and the questions you ask. Your review sheet is your notes. If you are going through your notes preparatory to coming to class that day or reviewing this lecture recording, and you don't see something in there that you're like, oh, I thought we talked about that. Or you see something, you're like, okay, but you can't explain it to yourself. You're like, oh, okay, Bowen's reaction series. That was, I can't remember what that is. I wrote down Bowen's reaction series, but I don't remember what it is. It's a good thing to bring the class that day and ask questions about. You want to make sure that your notes are ready to be the best resource they can be for your exam. Okay. Write down as much as you feel like you can or should. Okay, I won't tell you everything. I have had students who have written down everything. I told you about that one student who had a binder that thick of notes at the end of the semester, right? She literally wrote down every word I said for the entire semester. Yeah, I'm pretty sure she got carpal tunnel out of that, but she did pass my class. If that's your strategy, go for it. She did get an A. I'm not telling you have to do that to get an A. I have students who write everything in shorthand. If you do shorthand, make sure it's shorthand that is well written, like neat and orderly, so that I can actually piece it together and figure out what you're saying in your notes. I do periodically check them to make sure that things look good. But feel free to use shorthand if that's your preferred note-taking method. Find your own method, and if you don't have one, play around with it and find something that works. Maybe do some research online and find some good note-taking strategies, or ask a classmate. Okay? All right, so that's when your first exam is. It will be over Module 1, Lectures 1 through 7. We are going to have our silly geology movie night coming up. I'm going to be sending out a Google poll, a link to a Google poll, so you all can vote. If you're watching this later, obviously, today is September 5th, 2024. If you're watching this later, obviously, you can't vote. But if you are currently in my classes right now, you can vote on this poll, and we'll figure out a day and a movie that we all want to watch. It is worth extra credit. It's a good, fun time. We have it on Friday evenings, so we'll just meet here in this room probably about 5 or 6 o'clock. And then I'll just turn on the projector. Actually, to be honest, considering how often this one shuts off, you know, like blinks on and off, we'll probably be in the room next door. That one is also mine. That's a historical geology room. The screen is slightly smaller, but it doesn't shut off all the time. So that's what we would probably do. But we meet over there and, you know, just bring food, snacks, friends, family, whatever. Yeah, it's a good time. I think those are the only 2 announcements I've got, other than labs 1 and 2 have been assigned. Labs 1 should ideally be turned in by now. Lab 2, try and have it done today, because lab 3 you are getting today. And lab 4 you are getting on Tuesday. I know there isn't a full week between the assignments of lab 3 and 4, but that's the only day that really made sense, so that we could put more time in on Thursday for the exam 1 review. Okay, but you do still have a week for lab 4 and lab 3, even though I'm assigning them 5 days apart. Any questions?
Are we for the exam, are we going to be identifying rocks?
No, there will be no rock identification on this exam. This is a lecture exam only. You will get your lab exam later in the semester. Oh, thank you. Thank you. I do appreciate hearing I'm the best. No, so you have lots more time to prepare for that. All right. Good question. Anything else? Anything else you're dying to ask?
Burning
No?
questions, as they say.
Huh?
Burning questions, as they
Burning questions.
How do like animals get fossilized and not like rock?
How do animals get fossilized and not rock? How do you mean?
Because like if I die, or if someone like dies, then we just like disappear with the time.
You would decay. Okay, you bring up a very good point. When things die, their soft tissues do generally decay before they can fossilize. There are a few examples where that does not happen, a few rare examples. When we find preserved soft tissues, it's very rare. We call it a Lagerstätten. And those are extremely important for piecing together aspects of that organism's life cycle. We love it when we find that. Things like dinosaur skin, proto feathers on dinosaurs, muscle tissue, blood, stuff like that, usually gone. Very rarely are they found, which means that all fossils, or not all, but the vast majority of fossils that we find are from the hard parts of organisms, shells, bones, teeth, claws, things like that. Okay, that's what fossils are. And really all that's happening are there are minerals filling in the spaces, taking on the shape of that particular organism's hard parts. Okay.
So like becoming a rock.
Yes, it is becoming rock. And it's not that big of a transition because your bones and your teeth and all of that and the shells of animals, those are already made from minerals. Your teeth are made out of the mineral apatite. How many of you have found the mineral apatite in your lab so far? Good. It's one of the ones in there. Spoilers, I guess, if you haven't found it yet. You know to look for it now. But yeah, that mineral apatite, that's what your teeth are made out of. Okay? Your bones are made from mineral crystals. Okay? And so fossilization is pretty much simply the replacement of those original components with new minerals. Okay? Or additional minerals. Some of what was there originally does remain, which is why it's very valuable to use fossils for things like paleo-environmental reconstruction, like what I did for my master's degree, where I studied fossils and the isotope ratios in them that were put in there as that organism was growing to evaluate what the temperature and precipitation rates were for that part of the world while that thing was alive. Good question. Anything else?
Precipitation rates.
Precipitation rates, yeah. You can
That's
tell,
kinda crazy.
yeah, you can use carbon and oxygen ratios, carbon 12 and 13 and oxygen 16 and 18 ratios to tell things like temperature and precipitation rates. Yep.
Wow.
Okay.
The more you know.
No other questions?
And for me.
Well, let's dig in then. Let's begin. Lecture 6, Sedimentary Rocks. This is building off the back of Lecture 5, where we learned about weathering and erosion. Oh, no. Who can remind me what weathering is? Breaking down of? In this case, rocks, but really anything. When it's something is breaking down, it's a form of weathering. Good. What is erosion? The transportation of that broken material. Okay? Remember, we're going to use those two words in their proper context now. All right, so we figured out by studying weathering and erosion how sediment is made in the first place and how it gets moved to the places where it eventually ends up. Let's pick up from there. Sedimentary rocks are made from that sediment, believe it or not. Okay. Now, about 90% of the Earth's crust is igneous and metamorphic rock. That's not that hard to comprehend. We've got a whole bunch of stuff underneath the crust that really wants to be in a melted state, but can't because of the pressure. And as soon as it approaches the surface, guess what? It starts to melt, and when it crystallizes, it becomes igneous. there's also whole lot of heat. And something that you'll find out on Tuesday, the next time we meet, is that heat and pressure is causing metamorphism. Okay, so that's why we have so much igneous metamorphic rock. Okay, that leaves about 10% of the total mass of the crust to be sedimentary rock. Now, while 10% of the total volume of the crust is sedimentary rock, about 70% of all rock exposed on the surface is sedimentary. Why would so much of the rock exposed on the surface be sedimentary? Why isn't there that same ratio? Why isn't most of the rock exposed on the surface igneous or metamorphic? What's happening that's making all the sedimentary rock?
Erosion.
Those processes, weathering and erosion occurring on the surface, okay? The igneous and metamorphic rock is getting broken down, and that breaking down process makes that sediment, okay? Now, sedimentary rocks are very important to study. I've spent most of my career with sedimentary rocks as opposed to the other two. And the reason why is because it is in sedimentary rocks that things get preserved. Remember how you make igneous rock. Someone remind me how igneous rock is formed? In a volcano is one way, but what's happening to make that rock? What's cooling down? Magma and lava. That's how you get igneous rock. Do you imagine something dies and its bones get incorporated into lava or magma? Do you think that's going to come out the other end? No, that structure is going to be destroyed, okay? That igneous rock, the creation, the magma to igneous rock, think of that as kind of like a reset button. It melts everything, okay? Nothing of the original rock survives the melting process and then recooling down into igneous rock. Metamorphic rock, as you will learn next time, is a chemical and physical change that occurs inside of a rock because of heat and pressure. Nothing really survives that either. And so sedimentary rock is the only kind of rock that we can find remnants of Earth's past life. For example, the life that has occurred on Earth. We only find fossils in sedimentary rock, okay, as a prime example there. Also, evidence of surficial processes, things like, well, there were dune structures here. There used to be a lake here. All of that, that sort of evidence pointing to those conclusions can only come from sedimentary rock. Also, there's lots of resources in sedimentary rock. Things like oil are almost exclusively found in sedimentary rock, with a few examples different, right? Like that field in Vietnam we talked about, okay? But the source of that oil was from sedimentary rock, even though the reservoir that they're digging in for it is granite in Vietnam, okay? A lot of mining resources come out of sedimentary rock. We'll talk about these things, all right? So let's review our part of the rock cycle that has to do with sedimentary processes. We learned about weathering, breakdown, mass wasting and erosion. Those are the transport of that material. After that material stops moving, wherever it ends up, that is deposition, okay? It has been deposited in a location. It has stopped moving. After that is something called diagenesis. Diagenesis is the word that we use to describe anything that happens to that sediment after it's been deposited, but before it becomes metamorphosed. Diagenesis is any change that occurs to that sediment after deposition, but before metamorphism, okay? And that can include a lot of things. A lot of things can happen in that the boundary of diagenesis, one of which is it gets turned into a rock. We'll talk more about that process here in a little bit. First, let's talk about how we differentiate sedimentary rocks from each other. We have what are called clastic sedimentary rocks and non-clastic sedimentary rocks. Those are the two biggest classifications, okay? Clastic sedimentary rocks are made from the bits and pieces of weathered, mechanically weathered, broken down material. So you take an igneous rock and you break it down mechanically over a couple thousand years. You end up with a pile of sediment, and that sediment is going to go on to make a clastic sedimentary rock at some point, okay? The broken bits and pieces of other rocks, solid weathered products, okay? Then we have non-clastic sedimentary rocks, and there are a couple of examples for these. A couple of further classifications, I should say. Chemical non-clastic sedimentary rocks are made when the dissolved, which means chemically weathered, right, remains of other previous rocks reprecipitate. Can someone tell me what that means? What does it mean when something reprecipitates? Or precipitates at all? It forms and then falls, okay? Think of it like rain, precipitation, right? How does a mineral precipitate? Well, let's say that I have a water that is very rich in dissolved minerals. If I start evaporating a little of that water, let's say, then the concentration of dissolved minerals increases, and eventually you reach a point where the concentration of those dissolved ions is such that they start reforming solid products, and those solid products form. Have you ever dissolved salt water? Or excuse me, not dissolved. Have you ever evaporated salt water? What did it leave behind?
Salt crystals.
Salt. It's that process right there. Eventually, you evaporate so much water that the salt starts to form crystals again. The concentration has gotten too high. It can no longer be dissolved. Okay? Same concept here. And when that happens, you get a chemical non-clastic sedimentary rock as a result. Then we have organic sedimentary rocks. Organic sedimentary rocks are those made from the biogenic, they are made from biogenic components, okay? So a classic example of this, coal. What is coal made from? Plants, plant material, good, okay? Yes, coal does count as a rock, all right? It has formed, though, from previously living matter, and therefore it is an organic, non-clastic sedimentary rock. We also have certain types of rocks made from the shells and skeletons and body parts of other living things. That is also biogenic, and so those do count as organic sedimentary rocks. This is a matter of some debate, I should warn you. There are some people who say that the skeletons themselves were minerals before, even though they were part of an animal at the time. Therefore, should we really call these things organic? And the debate goes on. I am going to, for the purpose of this class, because it comes from an organism, I'm going to call those organic. Okay? There's no need to necessarily get you involved in a debate that won't matter for most of you. Okay? We're going to call those organic sedimentary, non-clastic sedimentary rocks. All right? Any questions so far? No? All right. Well, let's dive deeper on clastic sedimentary rocks. How do we tell common or classic sedimentary rocks apart from each other is something that I will go into on the next slide. But for now, I want to give you a brief introduction to what they are made out of. Okay? The most common ingredients of a clastic sedimentary rock are quartz and clay. Now, knowing what you know so far in my class, tell me, why would quartz be a common ingredient in a clastic sedimentary rock? Love the shirt, by the way, Jocelyn. Big Star Wars fan.
It was made slowly.
It was made slowly. That's not necessarily the case or the reason. What do we know about quartz?
Does it form under high pressure? Is that one? Or no?
No, quartz is actually one of the last things to form in the Bowen's reaction series. which does, in a way, play a part in this, if you go back far enough in the logic that I'm looking for here. Start with that.
Because it's like the waste.
The waste. Elaborate.
The last thing to form.
It is the last thing to form, which means that it is more what?
More light.
It is a light silicate, but that's not what I'm looking for. Quartz is one of the last things to form in Bowen's reaction series at the lowest pressure, at the lowest temperature in that magma chamber. Does that make it more or less stable than a lot of the other minerals at surface conditions? More stable. Good. So if quartz is more stable at the surface than a lot of other minerals, what will happen if I expose all those minerals to weathering? What won't break down? The quartz won't break down as quickly or as easily as the other ones because it is more stable under these conditions, right?
Okay.
And what does that lead to?
The creation of rocks with different minerals.
We're not there yet. We're getting there. What do I have a lot of left over after some weathering has happened? I have a lot of quartz left over. Most of my feldspars have broken down. My dark silicates have broken down. I've got a lot of leftover quartz. And that is why quartz is a very common ingredient in classic sedimentary rocks. Most of the sand that you see at the beach, that is quartz. Okay? Which, by the way, let's linger on that subject for a moment. Why would there be so much quartz sand on the beach, but you go further out into the ocean and all of a sudden there's almost no quartz at all out there? Why is there so much quartz sand on or near our coastlines?
The volcanoes are on the coast.
There are volcanoes near the coast. Water keeping it close to the shore. That's
As a
not the
process
big
of,
reason.
Like, weathering, being pushed out further.
What's
onto
being weathered?
I guess the rocks and the minerals are on that around the coast. Or
Yes,
on
and
the
that
coast.
they are part of a continent. What is the general composition of continental rock? What is the general igneous composition of continental rock? Basalt, and therefore mafic, is the general composition of oceanic rock, which means it has no quartz, right? What is the general composition of continental rock?
Sedimentary.
Feldspar is a mineral. You got the
Ferric?
first part of that right, huh?
Ferric?
Ferric means iron, huh? Felsic, good.
Felsic.
The general composition of continental rock is felsic. We learned that a few lectures ago, right? Felsic has lots of quartz in it, and therefore, as continental rock weathers down, quartz is one of the last things to weather. Therefore, the reason why we have lots of quartz sand on or near continents is because this is where the quartz is. It's not out in the ocean. You follow that logic train we just went through there? Okay, cool. Clays. Why are clays a very common ingredient as well in clastic sedimentary rocks?
Because if the one that is like on top, like
Where does clay come from? Let me ask you that.
the brick, like what is not the waste, it goes down.
It's far more simple than you're probably thinking.
Dirt.
It makes dirt. It is an ingredient of dirt, but where does it come from? Yes.
Soil.
Okay, so you're talking about the soil horizons. I'm talking about where clay comes from. We haven't made soil. Huh? What's weathering to make clay?
Non-solid breakdown.
You mean like chemical weathering? Yes, this is chemical weathering. Good, but what is chemically weathering to make clays? If it's not in your notes, it should be. Huh?
With silicates?
Silicate minerals. Most commonly, you said it earlier,
Felsic.
feldspar.
Oh.
And about 50% of Earth's crust is feldspar, right? So if about 50% of Earth's crust is feldspar and feldspar chemically weathers down into clays, boom, bada boom, lots of clays to get turned into classic sedimentary rocks. You follow that logic?
Yeah.
Okay, these ideas that you're learning, lecture after lecture, lab after lab, they build on each other each consecutive lecture. And we'll be going back and learning from those to learn the new stuff, okay? It builds on itself. That's why I have the class structured the way that I do, okay? So quartz and clays are the most common ingredients in clastic sedimentary rocks. We can have larger pieces of unweathered components. For example, feldspar. This piece of rock right here, this chunk of classic sedimentary rock, it's got a lot of sand-sized grains in there. That's probably a lot of quartz, but you can also see big chunks of feldspar in there. So these pieces were incorporated into this rock before they fully weathered away. Okay, that can happen. But the most common ingredients are quartz and clays. So now let's talk about how we tell clastic sedimentary parts apart from each other, rocks apart from each other, okay? The first thing is particle size, grain size, okay? How large are the individual pieces that my clastic rock is made out of? So we've got the scale here, and for those of you who have test kits in front of you, most of them have little grain size charts in there that you can see. They're marked very fine, fine, medium, coarse, and very coarse, and that's what you'll be using in the lab. Okay. For those of you watching this online, if you go to my lab videos, you will see that I put a picture of the samples next to one of those cards, so you can also see that. Okay. But let's start at the bottom here. We've got 1/256th of a millimeter and lower than that, so very microscopic. We call those clays. That is clay-sized. That is a clay-sized particle. So now you've learned about clay as an actual secondary mineral that is an ingredient in classic sedimentary rocks. And now we've talked about clay being a size. And normally, clay-sized minerals are, in fact, clays. Okay? But it's now also a description of size, is what I'm saying. Okay? And then above that, we've got from 1/256th of a millimeter to 1/16th of a millimeter. That is silt. If you have very good eyesight, like my wife is always reminding me she has and I don't, then you can see the larger silt-sized pieces. But if you put them on your fingers, you can kind of feel just the tiniest little, like feel the grains almost, like tiny, 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 okay? But you can feel them. Clay, it almost feels like a liquid. They're so small. Those grains are so small, okay? Have you ever felt flour? You know how flour feels slick and soft? That's tiny, okay? Think clay. And then we've got our silt, which is that next size up. And then from 1/16th to 2 millimeters is sand-sized. So when you tell me that this rock has sand-sized particles or grains, I'm going to think it's between that range, 1/16th to 2 millimeters. Above that, 2 to 4 millimeters, granules. 4 to 64 millimeters is a pebble. 64 to 256 millimeters is a cobble. And above 256 millimeters is a boulder. That's a nice boulder, right?
That's not just a boulder. It's a rock.
Okay. Now, any clastic sedimentary rock where most of the particles or grains are silt or clay sized, we're just going to generally call that, we generally classify those as mudstones. But other things would be called siltstone, claystone, shale. If you've ever heard the term shale, that falls in that category A lot of oil is formed in shales. We will learn about that here in a little bit. Okay. Earlier, just now, I said most of the particles are that size, right? What I mean by that? Well, very rare is it that you find a classic sedimentary rock that is 100% of one thing. Oftentimes, you're going to find some kind of range in there. And so we classify them based on what it appears that most of the grains represent. So it's very possible I could have a siltstone, and I'm going to call it a siltstone, even though I see every now and then there is a sand-sized grain in there. Even though there are some sand-sized grains, most of the grains are obviously silt-sized, so I'm going to call it a siltstone. Okay? I'll explain more about why that happens later on. Then we've got sandstone. You guessed it. That's made from sand-sized particles. Wow. I know. Mind-blowing. Now, once we move up from sand size, we move into the world of what we call conglomerates. A conglomerate is a mix of a whole bunch of grain sizes, but contains lots of particles larger than that 2 millimeter cutoff for sand. Okay? And there are two different flavors of conglomerates. I'll talk about those in a minute. Okay? Now, that's particle size, also known as grain size. Okay? Next up, we have sorting. Sorting is how many, all right? Sorting is how many of those particle sizes we have in our mix, okay? So, for example, I could have a very well-sorted sandstone. If I'm describing it as a very well-sorted sandstone, all I see are sand-sized particles. I don't see anything bigger or smaller. On the other end of the spectrum, I could have a very poorly sorted sandstone, which means that I've got a whole range of stuff from 2 to 4 millimeters. Okay? Or I could have just a sorted. It's sorted. I can see that there's a few in there, but it's mostly about 2 millimeters. You know, it's just there's a range there. Very poorly sorted, sorted, well sorted, very well sorted. Okay, there's that range that exists in there of how similar the sizes of your grains are within the boundaries of that particle size. Okay, and then there is shape, angular versus rounded. Remind me, when we learned about weathering and erosion last time, the more rounded something is, what does that mean? The more it's broken down, the more weathered it's been. Bingo. The longer it's been under the influence of weathering conditions. And so if I'm looking at a classic sedimentary rock, let's go back to our classic example of a sandstone. Okay. If I'm looking at a sandstone and I got my magnifying glass and I'm looking at them and I see that all of these grains are very well rounded. They're all spherical. What does that tell me about that sediment before it got turned into a rock? It could have been underwater, but that's a little more specific than I'm looking for. There is an increase in surface area as the particles get smaller for the mass as a whole. That is true, but not what I'm looking for. What happened to these particles before they got incorporated into this rock?
They got broken down.
For how long?
A long time.
A while. They were getting weathered for a good long while before they got turned into this rock. I'm not talking about the roundness of the rock. I'm talking about the roundness of the grains in the rock. If they are well rounded, that sediment went under a substantial amount of weathering before the process of turning it into a rock even happened. Now, this is cool for a couple of reasons. If I know that that sandstone is made from a sediment that was weathered for a long time, that sediment probably traveled a long distance to get there or was hanging out for a while. I can also figure out what minerals are in there, do a chemical analysis, a mineralogical analysis. I can do lots of things. I can figure out where that sandstone or that sand came from before it became sandstone. That sand came from a mountain 200 miles that way, spent a couple hundred years making its way down all those miles to eventually end up on this beach where it was gradually turned into the sandstone. I'm figuring out things about our planet, about our world, just by looking at these rocks and identifying these properties. Kind of makes us Earth detectives, if you think of it, right? The Sherlock Holmes of geology, if you want, right? It's pretty cool. We can figure out a lot of stuff by just observing things like this. All right. Actually, we can do the same thing with the sorting as well. Let me back up a little bit. Why would a rock be well sorted versus poorly sorted? Well, picture, if you will, you have a stream. The stream is going downhill with a certain amount of energy, carrying sediment with it as it goes, right? If it's a high energy stream, is it going to carry lots of larger or smaller particles? It's going to carry small ones, but it has a high energy. Does it take more or less energy to pick up a 50-pound weight versus a 10-pound weight? It takes more energy to pick up the 50-pound weight, right? So if I have a high energy stream, I'm also going to have large particles moving there. If it can move it, it will, right? Think about the flash floods we had in town not long ago. How many of you walked outside and saw stuff just floating down your street, right? Heck, there were a few small cars I saw floating at one point, okay? With enough energy, water can pick up a lot of stuff. Yeah, totally. So, if I have a high energy stream, it's going to be carrying large, medium, and small particles. What happens as I start to lose energy? Let's say that my stream is no longer going at a steep slope. It's leaving the mountain area and it's going out into a plain, let's say, where the slope is a lot less and therefore we are losing more energy. What happens as my energy drops? Yes, it will drop the heavier particles and keep the medium and the smaller particles. And then I lose even more energy. What falls out? The medium particles. And I only have the smaller particles that keep going. Okay? What does this allow me to do? If I see a stream bed deposit of rock, I know this came from a stream bed and it's made out of large particles. I know that I'm in the high energy part of that stream from long, long, long ago. I'm looking at rock from a high energy stream. And then I keep following that. And eventually I find the medium grained particle rock, right? I am following the course of the stream as it gradually lost its energy. That's what particle size can help us figure out about history. What about sorting? What happens if I lose all of my energy all at once in that stream? They all fall out at the same time. I'm going to have big grains and small grains and medium grains all mixed up with each other. It will make a, not necessarily a waterfall, because a waterfall, the river usually continues past the waterfall, right? But let's say a landslide into water, right? Let's say a landslide moves into a lake or a stream bed and then just instantly dumps everything right there. Okay? There are also underwater landslides that happen. And they drop, like everything moves and then all of a sudden everything just drops, loses its energy very quickly. Okay? You get very poorly sorted rock. There's a lot that we can learn by studying these few properties of classic sedimentary rocks. Okay. Let's talk about some of the more common ones. Shale. Shale is made from clay and silt-sized particles, very fine to fine, you would call those on your scales in your kits. Okay. We find these typically in very calm waters. Why would we associate with shales and mudstones with very calm water conditions? Low energy. Bingo. If we have high energy, the silt and clay, these very fine particles, are going to stay suspended in the water. Only when there is very low energy will these tiny particles sift down through the water and end up on the bottom where they can collect and eventually make that rock. Okay, well done. These includes things like lakes, floodplains, lagoons, and most of the time out in the deep ocean. Okay, where there is very little water in that water column, at the bottom of that water column. They tend to take on colors based upon their chemical content. So that includes things like if there's lots of carbon, like say there's a lot of living things that were in that sediment or in the water above that sediment that got incorporated into that sediment, you'll end up with a lot of carbon, and that's going to turn it black. Lots of iron content will make it red. Lots of chlorite content will make it green, so on and so forth. Depends on, the conditions in the environment. Because they are such fine particles that are gradually sifting out of the water column a little bit at a time to collect on the bottom, they tend to make these tiny, thin little layers. We call these laminations or laminae. Okay? And for anyone interested in the oil industry, these black shales are the most common source rock for oil.
I thought I recognized them.
Yep. Sandstones are made from what? What would you guess?
Sand.
Sand. Okay. No, I mean, don't laugh. I'll talk about that in a second. But yeah, sand-sized particles make sandstone. It's not always all quartz. If it's pure quartz, then we have a special name for that. It's quartz-arenite. It's very hard, very durable, okay? But there are other variations of sandstone, including one called arkose. Arkose is sand-sized particles, therefore making it a sandstone, but with 25% or more feldspar content. So there is a sandstone that is high in feldspar. We call that arkose, A-R-K-O-S-E. Okay? Then we've got another variation of sandstone called gray-wacky. Sometimes people will just call this wacky. Gray-wacky is what I learned, so that's what I call it, okay? But that's how you spell it right there. It is 15% or more silt or clay-sized particles in the sandstone. And this is a gray-wacky. I have been doing a tremendous disservice. I have not been passing these around as I talk about them. So I'm just going to back up a minute here, and I'm going to pass some of these up. Completely forgot that I had them sitting there. Okay, this is shale. Okay, I'm going to pass this around. I'm going to show this to the camera. You can see those tiny little lamination layers in there. Okay, this is very dark colored, which means that it has probably some organic content. I don't feel like it's lighter than it looks like it should be. Let's see, what else did we talk about? Sandstone. This is a pure quartz sandstone. It's got that almost solid white color to it because of its quartz. If you were to scratch this on glass, it would scratch it just like quartz. This has all the properties of quartz because every grain in there is quartz. Okay?
It's just compacted.
We'll talk about the compaction process, how you go from sand to sandstone, sediment to sedimentary rock. We'll talk about that here in a little bit. That is sandstone. Quartz sandstone, I should say.
Sandstonium.
This is arkose sandstone. Notice it's got this distinctive pink color. That's some feldspar.
Yay.
Okay? And you can see there are bigger chunks of it in there. Most of these fall within that sand-sized range, but you can see that there's quartz and feldspar in there. Okay? This is arkose. This is gray-wacky. Still sand-sized particles. Most of this is still going to be quartz, but you can tell, even just by looking at the color, that it's got silts and clays, enough silts and clays in there that it's thrown off the general look and the color of this sandstone. This is a gray wacky. Yep.
So not all gray wackies are necessarily gray.
No, they don't necessarily have to be gray. I've seen them from dark green to gray to brown. It just depends on the colors of what's in there. Okay. Next up, conglomerate. Conglomerates are made from the larger grain sizes. There it is. Okay. So larger than 2 millimeters. They usually have a wide range of grain sizes, but there is a substantial amount of those grains larger than 2 millimeters in there. True conglomerate, I will call it a conglomerate if those larger grain sizes are well rounded, like you can see here. Okay. Most of these grains in here have been substantially weathered before they got incorporated into this rock. Okay. This is a conglomerate. Held together, these bigger pieces are held together by lots of smaller pieces. Okay. Acting as a cement. Conglomerate. Now, I have a different name if those grains, the larger ones, are not weathered, if they are not rounded. Bless you. Okay? We will call it a breccia, B-R-E-C-C-I-A, breccia, if those large grains are still really angular, like you can see here. This is still a conglomerate, but it is a type of conglomerate called a breccia. Okay? You breccia, right? Is the most common joke there. I got that out of the way. Okay, but you can see, still held in place by the cement, but large, angular, jagged pieces. Okay? And again, the fact that there are large grain sizes here means that at some point there was high energy condition there that would move those pieces to begin with. How are we feeling? Any questions about clastic sedimentary rocks?
This is not a breccia, right?
No, that is the conglomerate. The breccia is the one with angular fragments. Yep.
Yeah. Angular fragments.
Yep. Any other questions about clastic sedimentary rocks?
All these individual pieces came from somewhere, from different parts, and the geologist
They could have come from the same place.
Really?
Yeah, they definitely could have.
I guess they're all kind of rounded, so it kind of makes sense.
The fact that they are rounded means that they were well weathered for a long time beforehand.
Could you make the assumption that they were weathered in the same place?
They could have been, or they could have been weathered on their way there, wherever they eventually got deposited. Weathering can occur on transportation or after deposition. Most of the time as well as being transported, because after deposition, they usually get buried.
Whoa.
Mm-hmm. Any other questions about clastic rocks?
I think they're good. You know, we don't have any tryptophobia people in here, right?
Huh?
It's a good thing we don't have anyone with tryptophobia in here.
You like the phobia of holes? I have that.
Do you really?
I do, yeah. I have to swallow it and just deal with it a lot of the time.
Thank you for your sacrifice.
Yeah. It's kind of ironic considering that I go in caves, but for some reason those don't bother me.
Is it because you know they're like
It's not the same. It doesn't feel the same. I guess you could say I have selective tryptophobia. But okay, let's move on to non-clastic sedimentary rocks. Okay, so we've got two classifications that we're going to talk about here. Inorganic chemical sedimentary rocks, which are made from the precipitation of dissolved minerals, and organic sedimentary rocks, which are made from the biogenic remains of something that was once alive. Okay? Starting with our inorganic sedimentary rocks. I already described to you that when you evaporate or remove water from a condition where there has been something dissolved in that water, it eventually is going to precipitate, fall out, reform. And then you get a bed of this stuff at the bottom of your body of water. And a classic example of this would be travertine. Travertine is a very common building material. Okay, it's a form of limestone. When underground water dissolves limestone, okay, then carries those ions away and eventually comes back out on the surface and warms up in the sun, or maybe it gets incorporated into a hot spring, or whatever the case may be, it's going to reprecipitate those ions back into a form of limestone. And so you get bed upon bed, step upon step, layer upon layer. This is travertine forming around a hot spring in Yellowstone. Okay, that water is hot. It's precipitating out.
Hot spring.
Yeah, that is a hot spring. That is forming around a hot spring. Out in the ocean, this also happens. I'll get to that in a moment. Okay? This right here, you see these little shells in there? Those are actually bits and pieces of an animal called a crinoid. They've been around for a very long time. They still live in the oceans. They have a very fascinating history that we'll go all about in 1404. But they're kind of like flowers. They have a long stalk and then a flower-like structure called a calyx on the top with tentacles that catch plankton out of the water. This fossil right here, this is actually a couple of crinoids right there, and you can see where the stalk comes up into that flower sort of structure. Okay. But the stalks are made out of tiny little discs that are piled on top of each other. And right here, this to me it looks like a bowl of Cheerios. Right here, like it looks like a bunch of broken Cheerios. So I call them crinoid crunches, but that's just me. It sounds like a paleontologist's favorite cereal. You know, I'm gonna have some crinoid crunches. I'm weird that way. If you have ever felt the inclination to chew on a rock, like if you ever looked at a rock and be like, that looks like it would be delicious, you're probably supposed to be a geologist. I'm just letting you know right now. Okay. Huh?
The urge.
Yes, every now and then I will see a rock and I'm just like, that looks like it would taste so good. And I mean, I'm not dumb. I don't break my teeth on rocks. It only happened one time, okay? Just drop it. All right, so limestone is very common, okay? It makes up 10% of all sedimentary rock on Earth is limestone, okay? Now, the inorganic version of limestone, we call this micrite. This rock right here, micrite. You won't be able to see any crystals in there, or if you do, they'll be very small. Why? Because micrite is made out of tiny little calcite crystals that precipitated in the ocean and then filtered down to the bottom and got incorporated into a bed that became this rock. Okay? This is inorganic. This has no life whatsoever made this. This is simply a chemical process in the ocean. What could cause calcite to precipitate out of water? Well, there's a few interesting things that you need to know about calcite. You've already learned a couple of them, right? This is the one that fizzes. Yeah, when I pass this around, feel free to open up your test kits and drop some acid on it, okay? It will fizz just like the calcite crystals I gave you for your lab, all right? Calcite has a few weird characteristics, one of which is most of the time when you want to dissolve something, do you put it in warm water or cold water? say you want to make chicken, like chicken broth. Do you dissolve your chicken bouillon in hot water or in cold water? You do it in hot water. If you want to dissolve something, you usually put it in hot water, right? Calcite, though, precipitates in hot water and dissolves easier in cold water. Yeah. Now, this is cool for a couple of reasons. That explains why we have so many micrite limestones forming in warm, shallow seas. Okay? But we have very little of it at the poles. Now, in the world of biology, this is cool, in paleontology specifically, because animals that use calcite for their shells tend to stay on the middle side of the 45th longitude, okay? From the equator about to 45th, that's where most of them hang out. Beyond that, okay, moving out closer to the poles, it's too cold. Limestone can't really form very easily because it's too cold, water's too cold. Calcite dissolves easier in cold water, and therefore shells made out of limestone or made out of calcite don't do very well up there. And so instead, those animals use silica ions to make their shells. And so as we go back into the fossil record, I can see a layer of rock that has fossils made from calcite shells and say, okay, fairly warm water conditions here. And I can go and look at a different layer of rock, and I can see that the shells are made from silica. I can say, oh, this was pretty cold water conditions during the time that these animals were alive. These are the silica-shelled animals that were succeeding here, okay? So we can use this little bit of information, this little factoid, for a lot of stuff.
Here you go.
Then we've got our organic limestones. And those are made from shells and skeletons and little bits and bobs from animals that grow their shells out of calcite that they pull out of the water. They steal those ions out of the water and make them for shells for themselves, okay? So you can see this is a fossiliferous limestone. You can see all the different shell structures in there. Fossiliferous, that's the word we would have for this, okay? Start that.
Limestone is like, so what would be like limestone?
Limestone is a type of inorganic sedimentary rock, I just showed you the inorganic one. It is a non-clastic sedimentary rock made from calcite and some variations of calcite.
Non-plastic equals like
No, so non-clastic means that it is made from dissolved ions. Whether those ions precipitated into crystals on their own or through a biogenic process, originally the material is from dissolved ions, chemically weathered remains, okay? As opposed to clastic sedimentary rocks that are made from mechanically weathered bits and pieces, okay? Yes, so I passed around that fossil limestone. Another variety of this is this guy right here. This is called coquina, okay? Think of this as pre-limestone, pre-fossiliferous limestone. These are pieces of shells that have started the process of fusing together. Their shells have been compressed, and the pieces have started to fuse together. So it's one distinct unit here, but it hasn't quite turned into a rock per se. It's a bunch of compressed shells, okay? This is coquina. And then we've got chalk. Come on, camera. Stay with me. Come on. Over here. Over here. There we go. Okay. Chalk. Any of you guys ever used chalk? Okay, right on a chalkboard. That's a type of limestone. Chalk is made from, see this little dust on my finger? Each little piece of dust is a microorganism. Planktons mostly. Planktons, coccolithophores, diatoms, radiolarians, all sorts of cool names for them. Okay. But each little piece of dust is a tiny microscopic shell. Yeah.
Where's Karen?
Yeah. Huh?
Where's Karen?
Where's who? What?
It was a SpongeBob reference.
Oh, I'm sorry. I watch SpongeBob. I'm sorry. I didn't grow up with it. Well, I would have. We just didn't watch much TV, so I don't get many SpongeBob references. There are a few funny ones I get, but I'm sorry I didn't get that one. That's why I'm a geologist. I didn't have SpongeBob. Now I know. Thank you. Thank you. That's where my parents went wrong. Okay. Okay. Good to know. I had no TV, so I played with rocks. All right. I'll go see my therapist later. Okay, so chalk is basically compacted, compressed microfossils. Okay, so I'm holding probably a couple billion microfossils in my hand right now in this chunk of chalk. Now, most of the time these days, when you go and you write with chalk on a chalkboard, it's chemical. It's like they made it in a lab. They squeezed it out of a tube and then let it dry out. Okay, it's not real chalk anymore. They just use other things to make it. Real natural chalk tastes a whole lot better. I'll just tell you that.
Taste?
Oh yeah.
You tasted both?
Yes.
You want me to say?
I'm not telling you to taste it. I'm just telling you that the real stuff tastes better than the fake stuff. These are the White Cliffs. These are in England. This is on the coast of England. Okay, the White Cliffs of England. This entire White cliff face, that's all chalk. That's a lighthouse for scale, by the way, right there.
Chalk.
This is all chalk. This was put down during a time when the sea life, when the oceans were filled with so many living things. Like if you went for a swim and you'd basically be like drinking soup. You would be drinking up so many little living things. Like I don't even know what the nutritional value would be, right? But during that time, all of this chalk was deposited. That's all microorganisms, just like that little piece that passed around. Almost an innumerable quantity of them. I can't even begin to estimate how many microorganisms are in that whole layer of chalk. 4 crabs?
1 fish.
And a fish. Probably a few more than that. Okay? At least 12. I think we can all agree on at least 12. Okay. Any questions about limestone? By the way, do you guys recognize this picture? Do you know where that is? That is the Guadalupe mountain range. Just out to our west. You guys ever hiked the Guadalupes? No? The entire Guadalupe mountain range is a coral reef. It is limestone, a giant mound of limestone sticking out of the ground. It's there because it used to be a coral reef when all of this was underwater. Okay? Yeah, that's why you go up there and you find fossils all the time. If you ever go on my YouTube channel and you watch my caving videos that I do in the Guadalupes, I've got a couple from there. I'll show you all the fossils in the cave walls as we go past. I'll tell you what they are from when that used to be a reef complex.
What's the nutritional value of chalk?
The nutritional value of chalk? Non-existent. You might get some kidney stones if you eat a lot of it, but that's fine. You'll get more kidney stones from drinking soda than you will from that chunk of chalk. Yeah. Don't drink soda if you don't want kidney stones. I'll just say that.
What type of stone is that?
A kidney stone? Oh, that's a good question. That would be a biogenic, non-clastic sedimentary rock. Yeah.
What that means, that it was made.
Just like the shells in that fossiliferous limestone, it was made by an organism. In this case, you. Very much like your bones, too. Think of it in the same context of your bones. Your body made it as as its own natural process.
What kinds of like stones can I eat?
Your body?
Yeah.
Gallstones, kidney stones. Those are the only ones that I can think of. Yeah. That typically happens when you have an acid imbalance in one of your organs, which is why soda is a big common cause of that. Okay.
So don't drink a lot of soda.
Don't drink a lot of soda. Yeah. I have a friend. He's someone that I help out with over the summer when I'm doing summer and I'm not teaching a lot, and therefore I'm not making a big paycheck from the college. I usually install sprinkler systems and artificial turf over the summer. And the guy that I do that for, he owns the landscaping business I work for over the summer. He has had 37 kidney stones, but he refuses to stop drinking sodas.
Jay,
Yeah.
drink a day then.
I see him drink them constantly. Yeah.
It's a new can every time you see it.
Huh?
It's a new can every time you see it.
Like a new can, yeah. Yep. Okay, moving on. Dolostone. Perhaps you will recall in no, we haven't talked about that yet. Okay. Perhaps you will recall in learning about minerals, I told you that there were a few minerals that react to hydrochloric acid. Calcite reacts strongly. Dolomite reacts very weakly and only if you powder it. Okay. Now, the reason why they share that similar relationship, and by the way, if you've already finished the lab, you'll know that they have almost the exact same properties. Okay. Why are they so close to each other? The only difference between dolomite and calcite is one magnesium ion that's just attached itself. That magnesium ion kind of gets in the way of a good acid reaction, but otherwise, the properties are almost entirely the same. Well, just like calcite and dolomite are similar, limestone and dolostone are also very similar. Think about that micrite I just passed around not long ago. And then as I pass this around, sorry, this is the wrong one. Is it? No, this is the right one. Okay. When I pass this around, you'll see that they share a lot of similarities. Okay. But if you drop acid on this, it's probably not going to have a very strong reaction because it's dolomite. It's made out of dolomite. Dolostone made out of dolomite. Easy to remember, right? Yeah. Now, how does dolomite come around? Well, we're still not entirely sure about that. It's essentially limestone with some magnesiums in there. Now, the most likely explanation that we know of, or that we can think of anyway, is that at some point, water infused with magnesium ions has to make its way through a limestone bed, and those magnesiums just attach themselves to the bonds. How or why? Not entirely sure. And it's really hard to test without, a couple 100,000 years to, utilize that hypothesis and see if it would work. So this is the best explanation we've been able to come up with so far. It's just got some magnesiums in there throwing it off. Okay. Then we've got chert. You remember when we learned about chemical weathering, and I told you about those silicon ions that separate themselves as part of the chemical weathering of silicate minerals? The silicon ions go and end up somewhere and form layers of chert or flint or jasper. I told you about that last time. Well, here is a chunk of that chert. This is microcrystalline quartz made from the chemical weathering byproducts of silicate minerals. Okay? Again, same properties as quartz, will scratch glass, so on and so forth. Chert is the rock that Native American populations would make a whole bunch of their spearheads and arrowheads out of. If you ever seen like knapped arrowheads, it's usually chert, especially in the north. They use chert a lot in the north. Over in New Mexico, California, Arizona, they had a lot of obsidian from old volcanic eruptions to work with. Down in Mexico, they used a lot of obsidian. Pretty much everywhere else out in the east and the north, they used chert.
Arrowhead.
Yep. Yeah.
What did you say chert is made by?
Chert is made when you chemically weather a silicate mineral. You'll usually have a few silicon ions left over. Those silicon ions are going to flow through the groundwater until they reach a void or a space that they can fill in or make a fossil out of. This is an agate. This is essentially a slice from what was a ball of chert that filled a circular hole in a rock somewhere. Okay? That's how you get an agate. That's how geodes form as well. Okay? Don't fall down. There we go. And then we have evaporate minerals. Evaporate minerals are things like salt and gypsum that form when water evaporates. Like, have any of you ever been out in Utah? Driven through Utah? Okay, you have? How was it a nice sunny day? No? It was cloudy? Okay. But how white was it? Very white. On a sunny day, you don't have sunglasses, you get blind driving through Utah. So much of Utah is just flat and white and just, it's all salt and gypsum basically that was left behind from a giant lake that used to reside over a substantial amount of the Utah Valley, the state of Utah, not just the valley, but Lake Bonneville it was called. And it gradually shrunk and shrunk and shrunk over the years. What's left is the Great Salt Lake, okay? And that is still shrinking. It's getting smaller and smaller all the time. But it left behind a whole bunch of salt and gypsum, making these sort of playas of all of these evaporate minerals, okay? All right. Now let's talk about coal. Coal is formed when you get, where is my chunk of coal? It's down there. It should not be down there. It should be up here. Coal is formed when plant matter, trees, weeds, horsetails, ferns, whatever the case may be, dies, falls over, and then lands in water that is anoxic. Can someone tell me what anoxic means? Huh? No oxygen or very low oxygen. Why would that happen? Well, if you have standing water, like say in a swamp where the water doesn't get renewed all the time, then the bacteria that start decaying plant life in that water are going to be sucking the oxygen out of that water. Okay? And eventually you'll reach a point where your water, not getting refreshed, is going to reach anoxia. Without oxygen, things can't decay. And so all your plant matter that keeps falling into this water doesn't decay very much. And so it just gets compacted and compacted on top of each other, not decaying, not getting eaten, not getting rotten away. And so you get all this plant matter that's compacted on top of itself. And eventually you reach something called peat. P-E-A-T. This is the first stage. You can still tell this is plant matter, right? You can still see the fibers in there, some chunks of wood. Okay? This is peat. You can burn this.
Burning rock.
Yeah, you can. I wouldn't recommend it. It'll smell awful. This is full of a whole bunch of stuff that would make your house smell pretty bad. There's a lot of sulfur in here. Okay? It's peat. Let's not do that. Okay? That is peat. The next phase, if you continue to bury that, it gets pressured up. It gets heated. We're going to cook it a little bit. You end up with lignite. Now, this actually looks like a rock. This is lignite. If you look closely, you can still see plant structures in there, imprints of wood, some things that might have once looked like leaves. But it's been so compacted. It'll probably take 3 feet of lignite or of peat to make a foot of lignite. It gets super compressed down. This will burn more efficiently than that peat will. It still has some stuff in there that you really don't want to let loose, though. Okay, a lot of bad gases and so forth. That is lignite, sorry.
Would it like explode or something? Or like,
No, it wouldn't explode. It'll just smell pretty bad. Not as bad as the peat would, though. And it'll release gases that are not very good for the atmosphere. All right, camera, stay with me here. Now, if you continue to bury and pressurize and heat up that lignite, that's when you get true coal, also known as bituminous coal. This is the stuff that powered the Industrial Revolution. They also used lignite, but this was the real kicker. The energy in this chunk of coal is way more than in that chunk of lignite, and is far more than in that chunk of peat. Okay? It's not going to smell good. No, it's coal, but it's gonna be a better thing to burn than that. Okay? A lot of the impurities in that have been cooked out of this. Okay, but it still has them. When you burn coal in like a coal power plant these days, most of the time, federal law requires you to have some sort of filter system to catch all of the nasty stuff that comes out from burning your coal. Most of the United States infrastructure still relies on coal power. I think it's like between 40 to 50% or something like that. It still uses coal power. There's a lot. Okay.
So like, it's not the same coal like burning wood. Like burning wood, normal wood.
There's far more energy in that coal than there is in burning wood. Now, there is another step beyond bituminous coal. This kind of enters the realm of metamorphism that we will talk about next time. But if you take that bituminous coal and you metamorphose it, so extreme heat and pressure, not enough to cause anything to melt around it or anything like that, but still extreme heat and pressure, you end up with anthracite. Yeah, that's pretty, huh? Yeah. Yeah, almost looks like obsidian, doesn't it? But no, this is anthracite. This is coal, but this is the cleanest, purest form of coal that you can find on our planet. This is one of the most efficient sources of energy. Probably the cleanest source of energy, of hydrocarbon energy anyway, fossil fuel, that exists on our planet.
Oh, it just broke on.
Hmm?
It just broke on.
Yeah, that'll happen. It's pretty soft. That's okay. Just pass them both around. Okay? Anthracite. Huh? Harder than the coal, yeah, definitely.
Ooh.
Now, why don't we use anthracite for everything, you ask? Don't worry, we'll get there. Okay. Honorable mention. There is a type of limestone . Why are all my sedimentary rocks ending up down there with my metamorphic rocks? There is a type of limestone I did not talk about before, but which you should know about, called oolitic limestone. Oolitic. Oolitic limestone is often confused for sandstone because ooids or oolites are spherical crystals of calcite that form in very warm, shallow seas, like around the Bahamas. Okay, very classic example. This chunk that I have, this bag and this chunk that I have, these come from the Bahamas. I'll pass these around in a minute. Yeah. But what happens is in a very warm, shallow sea where you have that back and forth motion of waves and the surf near all these islands, your calcite crystals precipitate out, they fall to the bottom, and then they go rolled back and forth and back and forth and back and forth. And as they do, they pick up more and more calcite and form spherical grains, okay, from that back and forth motion, that rolling motion. And then eventually those spherical grains do get mashed together through the sedimentary process and they make a rock. So here I'm going to pass around this bag. This bag is full of spherical oolites. These are made out of calcite. It looks like sand. It is not sand. And then this is oolitic limestone made from those oolites. You can drop acid on this and it will fizz, just like all things calcite. Okay? Don't open the bag. There is a small leak in it somewhere, I think, so don't hold it over a computer or anything. But this is oolitic limestone. All right. Any questions about non-clastic sedimentary rocks? Okay, let's go back to diagenesis for a little bit. Remember, diagenesis is any change that occurs to your sediment after deposition but before metamorphism. This includes a temperature range of about 150 to 200 degrees Celsius. That is the right temperature range for things to happen. What's happening? You're making rock.
Yay.
So between about 150 to 200 degrees Celsius and a few kilometers of depth, giving you enough pressure, right? That is when you start the process of lithification. Lithification is the word that is how you make rock. Okay? Lithification. When something is lithified, it is becoming rock. This happens through compaction and cementation. Compaction, the pressure is so high that it squeezes out the air and the water between all your grains of sediment and shoves them so close together that they start to interlock with each other. Cementation, that's when whatever water was there leaves behind cement, some dissolved ions. Perhaps it's calcite, perhaps it's silica, perhaps it's iron oxide. Something that is going to glue those sediments together. The better cemented it is, the harder it is to break that rock apart. Okay? That's lithification. Compaction and cementation to make sediment into sedimentary rock.
So compaction have water, but then
And you squeeze everything, all that air and water out. Typically, for most sedimentary rocks, it takes at least several feet of sediment to make 1 foot of sedimentary rock. That's how squeezed they are getting. A couple of feet of sediment makes a foot of sedimentary rock. Yeah, so it would take that much mud to make that much mudstone. You're squeezing everything out between the particles. So remember, we've got our clastic and our non-clastic sedimentary rocks. And you've got your chemical and organic, or your inorganic and your organic non-clastic sedimentary rocks. So how do we describe these things? We use things like textures, particle size, grain size, sorting, the roundness of your clastic grains. Your non-clastic rocks, they could be made out of crystals. They could be fossiliferous. They could be oolitic, organic, right? All these possibilities that we've learned about. These are how we differentiate them from each other. These are what you'll be learning or using on the lab. So, with what we know now about igneous rocks and sedimentary rocks alone, we can give some pretty detailed observations and interpretations about our world, right? I can tell a lot about the history of our planet just from what we've learned so far in this class. You can pick up a rock, and assuming it's igneous or sedimentary, tell me a lot about it, especially after you do the lab. Once you have some hands-on with that, you'll be able to do it like this, okay? This helps us to understand the application of the principle of uniformitarianism a lot more as well. Remember, principle of uniformitarianism. Physical, chemical, and biological processes that happen today also happened in the geologic past, right? There's that detective work coming in. you are familiar, a lot more familiar now, with these processes than you were before. And you can apply your knowledge of these processes to make interpretations of Earth's past. From swamps to glaciers, lakes, beaches, you are able to look at rocks that come from each one of these places and figure out where those things were in the world before. If I'm looking at a rock 100 million years old and it is a beach sandstone, guess what? There was a beach there 100 million years ago. Okay. Even though you might be in the middle of the United States now, there was a beach there 100 million years ago. Okay?
Crazy thought.
What?
Like the Guadalupe mountain, you said it was
Right.
used to be a forward.
Where that, yep, that all used to be underwater. Exactly. Okay. So now let's talk about sedimentary structures. Sedimentary structures are evidence of processes that have been preserved in sedimentary rock. Simple example, fossils. We'll talk about that in a moment. But there are other sedimentary structures. Mud cracks, for example. We all know how mud cracks form. Mud dries out, you make mud cracks. What happens if those mud cracks are then covered in sediment? They can get preserved in rock, and we can find them in that rock later. That tells me something about the environment. Okay. Ripples, like what you see at the beach or at a stream or at a lake in soft sediment that's being moved by water. You make those ripples in the sediment. Those ripples can harden, become and get buried and be preserved in that layer of sedimentary rock. Bedding planes. A bedding plane is when one type of sediment is deposited on another type of sediment. And so there is this natural separation between the two. That's a bedding plane, that's a bedding plane, that's a bedding plane, and that's a bedding plane. There may not even be that big of a difference. Maybe it's 0.5 millimeter in size. Maybe it's the sorting. Maybe it's the cementation quality. There is something different between that layer versus that layer versus that layer. Okay? Making these bedding planes, these differentiation boundaries. Cross bedding looks like this. We've got this sort of, it's going this direction, then it's going that direction, now it's going this direction, now it's going that direction, piled on top of each other. Anyone have an idea for what could make that?
Wind?
Wind is one way. Doing what?
Weather.
Hmm?
Weather.
No.
Like it goes one way, then it goes the other way.
What's it moving one way and then the other?
The mineral, the sediment.
Okay, yes, it is moving sediment. You're hitting good stuff here. Can you think of an example where wind is moving sediment one way and then another?
Storm.
Maybe a terrestrial environment. What is one huh?
River.
A river could do this, but we're talking about wind right now.
Tornado.
I'm not talking about the weather. I'm talking about what structure could get moved back and forth by wind.
Sand.
Tree.
Sand in what structure? We have a whole bunch of them not far from here. Out in Monaghan's.
Dunes.
Dunes. Wind moves dunes back and forth, right? And they'll go this way and they'll go that way. Well, as the dunes pile on top of each other and leave layers behind, they're leaving these sort of angled layers. These represent where the face of the dune was at one point. And then the wind blew the dune back another way, leaving them deposited on top of that in another direction. And then it blew it another way. And then it blew it another way, and another way, and another way, and another way, and another way. Cross-bedding, we call this, where either wind or water, yes, causes a change in direction in the deposition of sediment. And you can see how the changes in direction are piled on top of each other. Well, by looking at the angles of deposition here, I can retrace the steps that these dunes made. Pretty cool. And fossils. Let's talk about fossils for a minute. Fossils are a type of sedimentary structure. I've got some fossilized trees that I found up here in Montana. There's a tree right there. This one's kind of heavy though, so I'm going to pass around the smaller one. Huh?
How old is it?
These, dinosaur age. Cretaceous. Don't know exactly the age, but about the Cretaceous. Okay. You can see it still has the tree structures, like the bark imprints there, but every biological cell has been replaced by silica, microcrystalline quartz. This is now quartz in the shape of a tree, albeit a squished tree, right?
In the shape of a tree.
Yep. Some other cool things that I found. All of this is stuff that I found in Montana. That's not the only place I've done digs, but it's just where I took these pictures. This is a Tyrannosaurus Rex rib right there. This is a turtle shell. This is about the same size as that turtle shell. And then right underneath of that turtle shell, I found these bits and pieces of bones, which I after putting them together, I figured out this is the eyebrow of a triceratops. Okay, so I had the brow ridge and the socket around the eye. Okay. However, this is kind of an embarrassing story because I took this picture. I was so excited. I took this picture, and then I decided, you know what? I'm just going to do some digging around, some poking around underneath of this, and I found the rest of the skull, triceratops skull, exposed about half of it, and then, being the dummy that I am, forgot to take a picture. And then it was time to go home because the dig season was over. And so I had to kind of, when you're a paleontologist and you only have a certain week window, usually permits are for 2 weeks or so to go dig. So I only had a certain amount of time that I could dig, right? I found this on the last day of the dig. I did not have enough time to excavate it before I had to leave. So it's pretty common practice to do this. I couldn't dig it out, but I covered it. I put a sort of like small tarp section around it, covered that in dirt to make sure it wouldn't blow away. And then I logged the coordinates and I gave it to the next research team that were going to be there the next summer. So hopefully they went and excavated it at some point. This was back in 2019. Okay, hopefully they went back and excavated that. But when you don't have enough time to do something right, dinosaur bones are too precious to get wrong. So you just leave it alone and let someone else who has the time handle it. Okay.
Makes sense.
Yep. Now let's talk about mining in sedimentary rocks. Remember that most of our crust is silicate, right? Silicate minerals. So when we're talking about non-silicate resources, those are things that are kind of just incorporated into sedimentary rocks, okay? They fill in the spaces between grains like oil or water do, okay? So limestone is a non-silicate rock, right? But we use that for a lot. We mine limestone a lot. If you're ever going down a crushed rock road and it's that sort of gray rock you see all over the place, that's limestone, okay? That's crushed limestone. Very common, very easy to crush. It is soft. Very commonly used for stuff like using roads. You can also use it for building material, okay? You can crush it into powder and use it to neutralize acids in soils, like that story I told you all last time, okay? Gypsum, we use that as drywall. If you've ever installed drywall or broken a piece of drywall, that fine white dust that's in the drywall, that is gypsum, okay? They have that in there because it's excellent at absorbing water. It keeps moisture out of your house better. Different aggregates for things like cements and concretes. We would usually grind up things like conglomerate or sandstone to make those. So sedimentary rocks are very commonly used for mining resources. In addition to that, a whole bunch of other stuff is found in sedimentary rocks. Salt, sulfur, Garnet for for industrial abrasives. Same with corundum, but you can also use that for gemstones, right? Clays, apatite, all of these things that we use can commonly be found in sedimentary rocks. The gold mine that I worked at, we were digging through sandstones, okay? And some cherts. Okay. Most of the energy that we get comes from fossil fuels, the vast majority of it. 23% coal, 24% natural gas, 37% petroleum. Nuclear only amounts for about 9% of our energy. We have about 104 operational nuclear reactors, I want to say, in the United States. But that only accounts for about 9% of nuclear power, and 7% of it is renewable. That includes biomass, hydroelectric, geothermal, wind, and solar. I don't know how many of you have been paying attention to politics for very long, but do you recall someone at some point in some presidency almost 4 years ago saying that they wanted the United States to be fossil fuel independent by 2050? Do you remember that lofty goal? No.
George Washington?
No, he was a little more than 4 years ago. No, it was our current president. His whole thing was, actually the entire Democratic Party's whole thing was energy independent. I'm not going to wax political here. I'm just going to say that politicians don't like math because math proves them wrong a lot. Whether they're Democrat or Republican, politicians don't like math. They don't like scientists who tell them the math. Very few bureaucrats do. Because what they want people to believe is they have the answer to everything because that will get them elected. If a politician says, here is a problem, I know how to fix it, you will vote for them out of concern, self-preservation. Okay? But what if they don't really know how to fix it? You won't know until you give them a shot, right? And now they're in office. Okay? Well, here's the math. Only about 16% of all the energy that the United States uses is not fossil fuel based. How are we going to make up the other 34% to get 50-50? Are we going to do that by 2050?
Absolutely not.
No, we are not. The resources just aren't there. To make enough wind farms to power only the houses in the United States, only the houses, you would need to cover an area roughly the size of the state of New Jersey in wind turbines. Now, that's not a very big state, but it's still a lot of area. You should do it? Just get rid of Jersey? Yeah, I won't complain. Sorry if any of you watching this later are from Jersey. But if you also wanted to power all our infrastructure for industries, mercantile, grocery stores, shipping, if you wanted to power everything in the United States as it is now, you would need to cover Delaware, Massachusetts, New Hampshire, all the rest of the small states over there. You would need to cover that an area that size in wind turbines as well. Every square inch of it. That may not seem like a lot on the scale of the United States, but think about how much metal and resources that is. Sure, we could do that. We could put all those wind farms all over the place, but wind is inconsistent, right? What if you can't power your refrigerator unless, you know, a wind farm 20, 30 miles away has wind? What if there's no wind for a few days, right? Also, are you going to strip mine our planet to get that many resources to build all those wind turbines? Are you ready to do that? No, there is no easy answer here. Energy independence, fossil fuel independence is not as easy as politicians would like you to believe. The answers are not easy. We cannot simply drop fossil fuels like a sack of potatoes just because it's screwing with the environment. There's no denying it is, but it's not that easy to get rid of it. Okay? That's what I'm trying to put home here. 5,713 kilograms of stone, 178 kilograms of salt, 249 kilograms of iron, 11 kilograms of copper, 3,500 kilograms of petroleum, 3,700 kilograms of coal, 3,850 kilograms of natural gas. That, among all the other figures, all the other amounts there on this diagram, is how many natural resources each one of you Americans uses in a year. Whether you realize it or not, that many resources goes into upkeeping you and your quality of life in the United States every year. There's more than 350 million of us. Yeah.
Man, we like salt a lot.
Well, that salt includes the salt that you consume. It includes the salt that goes on roads to keep you safe. This is averaged out, but this is about what it comes down to keep you and our state of living here every year. That is a lot of resources. And who do you think finds those resources to maintain this quality of living? Geologists. Right? It's one of those careers, one of those sciences that will never not be needed. Okay, let's talk about coal for a second here. This is a distribution of the coal resources in the United States. Everywhere you see that is red, that's that nice bituminous coal. That's what we usually use in our coal plants. This orange, that's bituminous, and this brown, that is lignite. We use those far less often because they don't burn nearly as cleanly. You can see our Appalachian Mountain Range, tons of coal out there. That's why there's all those mountaintop removal coal controversies out there. We got a lot of red coal out here. Up here in the Dakotas, Montana, moving up into Alberta, there's a lot of lignite. Okay. Do you see the anthracite on there?
Yes, three little specks.
Yep, here, there, and there. And that, my friends, is why we cannot simply use anthracite for everything. It is the cleanest burning, least contaminating, polluting fossil fuel there is. Why don't we use it for everything?
It's expensive to make.
There's not much of it at the surface. The conditions that make anthracite happen so deep underground that for anthracite to come back up to the surface is pretty rare. And that's why there's so little of it. Otherwise, we would use it for everything.
There's no way to just make more of it?
Oh, you can. Yeah, we can make anthracite, but the amount of energy that goes into making it is extremely inefficient for getting the energy out of it. What good does it do for you to put, I don't know, just throwing some numbers out there. Let's say I put 20 units of energy into something, only to get 21 out of it. Sure, it's net positive, but why would you invest the 20 in the first place? And where do you get that energy in the first place? Burning coal.
Burn coal to get more coal.
Burning coal to get anthracite. Is that going to help the environment? I don't think so. No.
So you just gotta get it naturally.
Mm-hmm. Yep, natural. But there's not enough of it that's at the surface naturally.
We'll find more over here,
You're going to go find more?
Yeah.
Good. You're going to be a geologist. That's what I just heard.
We have to destroy New Jersey.
Destroy New Jersey? You're just stuck on that idea now. Just wipe Jersey off the map. Give us a wind farm. Okay, so the last thing I want to talk about before we move into lab time is the creation of hydrocarbons. Okay, I'm going to really simplify this. You get a bunch of living things in the ocean. Okay, let's say this is 300 million years ago. Okay, oceans full of life, microorganisms, planktons, those cicalophores, radiolarians, diatoms, all of those things. Okay, they live in the ocean. They die. Their bodies fall down to the bottom. They get incorporated in the fine-grained sediment there. Over time, that fine-grained sediment gets buried by more and more sediment and turns into shale or some other mudstone. Those once living things whose remains are trapped in that sediment get heated and pressurized. We call this cooking in the oil industry. We just generally just refer to it as cooking. Okay? It gets cooked for a while, and those hydrocarbons are rendered into a liquid. This liquid we call petroleum. Okay, crude oil. If You stick your straw down in there, whoop, you can pull that out. It's under its own pressure that deep underground, and you get that black gold coming out through your well. However, if it gets cooked too long, it becomes natural gas. Natural gas is just petroleum oil that has been cooked too long. Okay? Oil is more efficient to burn. You get more energy out of it. However, there's far more natural gas. And that's the sad truth of it. Unfortunately, we usually just get rid of the natural gas. You ever seen the flares going off? Technically, flaring is illegal in the state of Texas, but you can get a special permit to do it. Some companies do it without the permit and just pay the fines, and other companies get the permit and just flare. But it's supposed to be illegal because all you're doing is burning the natural gas because it is less efficient. Just because it's less efficient doesn't mean that we shouldn't find a way to use it. We burn off dozens of trillions of cubic feet of natural gas in the United States every year because we have nowhere to put it and nowhere to use it. The oil is more efficient, you get more energy out of it, and therefore that's what everyone's worried about. But if we could find some way to use that natural gas, gosh, how many problems would we solve? Sure, we'd still be polluting the atmosphere, but it's getting polluted by burning it off anyway.
Yeah.
Let's use it and at least solve one problem, you know?
I'll take that into consideration when I enter the field.
Petroleum engineer over here, please do that. Okay? All right, any questions about this?
No.
All right, well, that's where we will end it for today, and we will move into lab time. Lab 3 is going to be assigned. Let me pull up the PowerPoint. The PowerPoint is not very big. Just, the usual, just a quick run through of things we already talked about. Wow. Okay, I'm just going to breeze through this real fast.
Yes, sir.
Okay, I already talked about the common ingredients in these, calcite, clay. I already talked about that. Okay, so this will be a helpful slide to you. Okay, it's going to remind you about the classic properties that you want, your grain size, your rounding, sorting, all of that. Cementing quality, that's how easily does it fall apart, your classic cemetery rocks. If you can rub your thumb on it and stuff's falling off, it's not very well cemented, is it? But if you're knocking it on the table and nothing's falling off, it's pretty well cemented. Same thing, you do that with I do this in the videos. You can see if anything falls off of the clastic rocks. Then you've got your non-clastic rocks. What sort of textures do they have? Is it crystalline, skeletal, or oolitic? Just a few examples there. Then you've got any structures. Do you see any structures in it? That includes cross bedding, graded bedding, where you see that progression of large grains to small grains on top. Ripple structures, mud cracks, fossils. And then I just kind of have a list of some of the more common ones. Sandstones, shales, limestones, yada, yada. 12 samples and a few questions. Any questions about the lab?
No, sir.
Okay. Well, I'm going to end the recording here, and we can move on to lab time.
11 questions, 11 rocks.